Language models are learning to rewrite their own minds, ushering in a new era of self-improving AI. Traditionally, large language models, LLMs, like GPT-4 or Gemini, are powerful but fundamentally static. After initial training, their neural weights remain unchanged, unable to adapt in real time to new information or tasks. This rigidity has limited their ability to evolve and refine skills without manual intervention and costly retraining. Enter the innovative SEAL, Self-Adapting Language Models framework from MIT, which flips this paradigm by allowing LLMs to generate their own training data, critique their performance, and permanently update their internal structure, essentially learning to learn, much like humans do when they take notes and study from them ahead of an exam. The process at the heart of SEAL can be understood through a student and teacher analogy. In the MIT paper, the same model acts as both the teacher that creates new educational material and the student that learns from it. But future iterations could separate these roles for even more sophisticated self-instruction. The core mechanic involves the model encountering a new input, generating a self-edit tailored to address its knowledge gap, and using that output to fine-tune itself. These edits might reorganize facts, tweak hyperparameters, or invoke augmentation tools, leading to lasting updates in the model's neural weights. Critically, a reinforcement learning loop scores these self-edits based on downstream task performance, rewarding those changes that yield the greatest improvement, mirroring how learners adjust study strategies based on test results. The analogy to human learning is deliberate and instructive. Just as students distill lectures and readings into personalized notes that make sense to them, SEAL enables models to synthesize, restructure, and internalize new data in ways most beneficial to their unique brains. Unlike the laborious top-down process of feeding LLMs canned data, SEAL's approach empowers models to become both the architects and beneficiaries of their own instruction, iteratively closing the feedback loop of understanding with every new encounter. This strategy has impressive results. For instance, when applied to integrating new factual knowledge, SEAL-generated synthetic data outperformed both standard self-supervised data and even data generated by leading models like GPT 4.1, boosting question-answering accuracy from 33.5% to 47% on the challenging ARC-AGI benchmark, an exam intentionally easy for humans but difficult for static LLMs. The breakthrough comes from SEAL's two-loop structure. An outer loop uses reinforcement learning to optimize the process of composing effective self-edits, akin to a teacher learning to teach better, while an inner loop implements those edits using gradient descent, continually nudging the model's weights toward greater expertise. This recursive improvement mirrors the fundamentals of meta-learning, where a system learns how to learn. Notably, emerging research suggests these models might not even need traditional external rewards for reinforcement learning. Rather, their own confidence estimates could serve as internal signals for progress, accelerating the evolutionary cycle of AI self-improvement. Such an accelerated cycle is increasingly urgent as we reach the practical data wall, the exhaustion of high-quality human-generated text for training. Future LLMs will need to bootstrap their own development by inventing and exploring synthetic data landscapes far richer and more diverse than any single human curriculum. This is not far off science fiction. Related advances like DeepMind's AlphaGeometry 2, which trained on vast synthetic math problems, nearly won gold at the International Mathematical Olympiad, showing that massive-scale self-generated data can match or exceed the results of purely human-crafted practices. What's truly paradigm-shifting about SEAL is its broader potential. Rather than remaining static performers limited by their initial data diet, LLMs equipped with structured self-refinement routines could become dynamic agents, continually absorbing experience, incorporating feedback, and evolving during the course of extended interactions. Today's AI agents succeed at short, narrowly scoped tasks, but struggle with sustained, long-term objectives, because they cannot incorporate lessons learned along the way. SEAL's persistent self-directed learning changes that. After an interaction, the agent can synthesize a targeted self-edit and update its weights, building a richer, more relevant memory over time, much like a human employee accruing knowledge with every new challenge on the job. The implications reach far beyond simple question answering. With continual self-modification, AI agents could finally achieve adaptable, long-horizon coherence that matches their superhuman abilities at short tasks. This could drive the next generation of autonomous systems, AI that is not just a fast learner out of the box, but a lifelong learner, adjusting and specializing to the tasks and environments it encounters without requiring constant human oversight. Key takeaways. SEAL enables language models to generate, critique, and learn from their own training data, permanently improving themselves. This approach uses reinforcement learning to optimize edits and achieve superior performance on benchmarks traditionally tough for LLMs. Synthetic notes, crafted by the models themselves, can outperform expert-curated or GPT-generated alternatives. Progress in self-adaptation is vital as high-quality human-generated data becomes exhausted. Continual self-refinement promises truly agentic AI, capable of learning, remembering, and evolving across complex, extended tasks. In transforming how machines learn and remember, self-adapting AI may soon rival the very adaptability that sets human intelligence apart.